Welcome everybody. I'm very happy to open this event. I am Maria Pina Limongelli, Associate Professor of Seismic and Structural Engineering at Politecnico di Milano in Italy.
And I'm Salvatore Di Bernardo from a consulting engineering firm, Siorba Group, based in the United States.
There will be a short introduction of IABSE to open the webinar and a description of the duo webinar. And then we will leave the floor to our two speakers today, Professor Costantino and Dr. Zhu. I leave the floor to Salvatore, who will present IABSE, but I will show my screen.
So I would say a few things about the IABSE, International Association for Bridge and Structural Engineering. The name, I'm hoping that a lot of people are members, but I'm also hoping that we have non-members that will consider knowing more about our association. You can go to the next one. The mission of IABSE is to exchange knowledge and advance the practice of structural engineering worldwide. And this is a good example. Today's event is a good example of what we do. One of the thing that defines us is the international participation. So we have 100 countries represented in IABSE with over 2,500 members. Some of the highlights of what IABSE does, there are several publications that are managed by the association, a journal, bulletins, and conference proceedings. Conferences are the most important events that we do. Things have been changing lately, and we do more online-based event like this one. The association is organizing national groups and task groups. So pretty much all the 100 countries have national groups. Some of them do some joint activities. And we try, at the local basis, to be very active with our community. These are highlights of some of the most recent events. So you can see that there is a lot of activity worldwide. And then technical commissions and task groups are the core of the association, in which there is research, exchange of ideas and scientific contribution along the tasks that you see listed here. We have 6 technical commissions and 45 task groups. Talking about future events, as of now we have the next one will be an in-person event, will be Prague in May, in a few days. And then the next major event will be the Congress in Nanjing in September of 2020, this year. So, and then we have a very strong young engineer program. We encourage younger people and students to join the association and appreciate the value of what we do from a technical point of view and academic point of view. Thanks. You want to say something about Commission 1?
Yes, this event is organized by Task Group 1.9, which is one of the task groups of Commission 1, which deals on performance and requirements. And there are 9 task groups, as you can see here. And the dissemination of which this webinar is a part is in charge of Task Group 1.9. Specifically, this event is one of the duo IABSE webinars that are events that aim to provide a forum to present and discuss hot topics related to bridges and structural engineering, which is the focus of IABSE. And this particular format is based on a discussion between an academic, and today we have Professor Costantino, and a practitioner, and we have Dr. Zhu, who bring different perspective, and this makes usually a very lively discussion. At the end, also the participants to the event can integrate the discussion. There will be a Q&A session at the end, and you can post a question in the Q&A during the event. We will read them and ask the question to the presenters. Specifically, this event today is on seismic isolation, as you already know, of course, and the two speakers will talk about concepts, research, and outstanding applications. And the content, let's say, one of the focus of the event will be the description of the Beijing Daxing International Airport, which was recently awarded as outstanding structure by IABSE. And here you see some of the topics that will be tackled by the two presentations, but there will be even more with respect to this. Very important point, the presentation after the event will be uploaded on the IABSE e-learning page. If you don't know, it's important, it's an interesting point. IABSE has an e-learning page where you can find videos of webinars like this and much more. And also the webinar will be telecasted live in Facebook. We have a sponsor, Seismic PS. Seismic PS is dedicated to the development and application of advanced seismic protection technologies, and you will see more now in a video of our sponsor. Maybe Firat can help with this. So, okay.
So, Maria Pina, I can
sorry, I take some time to share the screen again. Now, Salvatore will present our speakers.
Yep. So we are ready to go, and I want to. My pleasure is to introduce Professor Costantino, who is the first speaker of today's presentation. Professor Costantino is the Samuel Capen Professor and also a State University of New York Distinguished Professor. He's at the University of Buffalo, New York. He's the editor of the Journal of Earthquake Engineering and Structural Dynamics, the recipient of the 2015 ASCE Newmark Medal, which is a very highly regarded award. And he's been, during his career, he's been focused on seismic protective system, earthquake engineering. He has published over like 300 papers. He's been involved also on the private side doing consulting work or peer review for like several projects worldwide. So it's an honor and a pleasure to have Professor Constantinos with us today, and he will be a source of great information about earthquake protection and seismic isolation of buildings and other structures. So without further ado, I think we are ready for you, Professor Constantino.
Well, thank you for the introduction, and I'm very pleased and honored to participate in this event. Let me start. Okay. Can you see the screen properly?
Yes, very well.
Very well.
Because I have, okay. Well, the presentation is on seismic isolation, an overview of concepts, implementation, and related research. Of the many seismic protective systems you're aware of, I will concentrate only on seismic isolation, and for that only for specific systems that have found widespread application, and including some with viscous dampers in them. So we have elements of passive damping, but I'm not going to talk about other things, that are so many. So I will go over a description brief of seismic isolation principles and its most widely used systems, some implementations in buildings and the infrastructure. Actually, I will show a couple of bridges since the IABSE has something to do with bridges, some research results that are of significance related to seismic isolation systems. Since I'm making the presentation, I will put emphasis on work that was done at the University at Buffalo, and I will show projects in which I was involved. I cannot talk about what others have done, but the scope at the end is to demonstrate the maturity of the technology and the range of its application. And I want to acknowledge many of my colleagues and sponsors. Since this presentation will be available, I will make a version of this available to all participants after the seminar. Therefore, I'm not going to dwell on some of the details of the slides or going over each individual person contribution in this slide. Now, seismic isolation is a method of construction and a technology in which a system is used to provide period lengthening and ability to dissipate, absorb energy, characterized by flexibility of the isolators, results in force, acceleration, reduction, and as a result of that, increasing displacements, which are concentrated in the isolation system with small structural drift. I will be talking about isolator displacements of the order of 500 to 1,000, and even more than that, millimeters, so 1 meter of displacements, hence the need for damping. And I will elaborate a little bit why we're talking, or at least in the United States and the projects I was involved, about 1,000 millimeters plus of displacement capacities for the isolators. In typical analysis of isolated structures, you're going to use 7, nowadays 11, but let's say 7 to 11 ground motions, triplets, that's X, Y, and vertical, to estimate isolator displacements. They are good at estimating median or average values. But uncertainty in the response and requirements that you have acceptable collapse risk determining the displacement capacity of the isolators. As an example, I take this case in which analysis gave a displacement demand in a median sense of 350 millimeters, but the displacement capacity of the isolator is provided as 700 millimeters, twice as much. There is something related to this, in an application, and that is actually in one of offshore platforms. You are going to see images of that in Sakhalin in Russia. Now, if the uncertainty is quantified by the dispersion in a normal distribution. And we assume the dispersion to be 0.3, which is rather low. It's more characteristic of motions, ground motions in California. The probability of exceeding the 700 millimeter capacity is 1%, which is pretty low. But if the dispersion is 0.7, then the probability of exceeding that is 16%, which is unacceptable. So the isolator has to be made even bigger to have acceptable collapse performance. And dispersions of this order are characteristics of motions, because uncertainty in the ground motion drives everything. Are characteristics of motions in, let's say, South America, in the northwestern United States and Canada, in Japan, for example. Now, of the isolators I will discuss something about are lead rubber isolators, friction pendulum type of isolators. We have several versions of those, and viscous dampers. I will start with this, a very good example of a hospital in Turkey built, completed some 15 years ago. And to get an idea, of the isolators in this case, they are almost 1.2 meters in diameter, and they have a displacement capacity well above 500 millimeters. 500 millimeters is the displacement computed in an average sense in the maximum earthquake. So there are about 400 isolators, actually 386, and there's a mixture of lead rubber and rubber isolators. A characteristic of these isolators, the lead rubber, which is a very successful system, is ability to dissipate energy. And you can see this with this force displacement loop in the horizontal direction, of course, that indicates a large ability to dissipate energy. The area enclosed by the loop is significant. I will point the strength as being about 10% of the weight carried by this isolator. And you can see, very important, that it changes from cycle to cycle as a result of heating effects, which need to be quantified, in testing. And this particular result is from prototype testing of the isolators for that project. The temperature of the bearing affects the behavior of the bearing, not only in terms of the heating effects, but also in terms of a direct effect on stiffness and strength, as we look at effects for a bridge in bearings used in a bridge in the United States, actually in the state of New York. You can see approximately a 65% increase in the strength of the bearings when we look at the effect of temperatures between 20 degrees and minus 26 degrees Celsius over a period of 2 days. Now, the exposure time is very important and depends, of course, the effects depend on the size of the isolator. For example, these were small isolators for a bridge because the displacement demands were small. This is in the state of New York. But if this were somewhere in Canada, it may have been prohibitive, actually, to use the isolators because the exposure to low temperatures is significantly longer, resulting in more effects of the low temperatures. The effect of the temperature can be understood by looking at the force stress strain curves, of lead. In this case, is pure lead in tension under some kind of dynamic conditions, actually. That this type of results are used to develop models that predict the behavior of these bearings. Switching now to friction pendulum bearings, we start with a single surface friction pendulum isolator. This is an image from our lab in 1988. And actually, this particular isolator you see now open, I have it here in front of me in the office, still functional. And this is one of the largest ever made isolators. I will point to this 700 millimeter displacement capacity, having in mind what I earlier mentioned about the why these displacement capacities are so large. This isolator carries a gravity load in one of the applications that is just over 10,000 tons. That's per bearing, and including the vertical ground motion effect, 13,000 tons, which is exceptionally large. And one may wonder, how can someone test an isolator like this? Well, I mean, you cannot test it at full scale dynamically, so something else has to be done. To give you an idea why something like this was used, an isolator like that was used in that platform that weighs about 40,000 tons. These are two of those platforms, and it can give you an idea of what exactly, and you can see the weights of these two. But there's a third one, which is heavier even. And understand the effects of the various loadings that one has to consider, from temperatures, low particularly, to snow, which is exceptionally high. Snow and ice accumulation is much more than anywhere we design, for example, in the United States, except up on the mountains of the Western United States. But most important is actually sea ice. To give you an idea of the effect of that, the 1 year return period force on each leg of the platform, and there are 4 legs, is 100 and a little bit meganewtons, so 10,000 tons, which is actually more than the gravity load. So isolation, seismic isolation, is not used to protect the substructure, the gravity, concrete gravity base, but actually to reduce accelerations in the secondary equipment in the structure above. And to give you an idea of that, in low-level earthquake, for which the facility must remain operational, you can see reductions of accelerations that are significant by a factor of approximately 2. Is not 10 that some studies, show, coming typically out of universities, but is significant enough to consider seismic isolation. There are also other effects, like allowing for thermal expansion and contraction and reduction of the stresses. You have to realize that this is 100 meter by 100 meters expansion and contraction from minus about 40 to plus 40 degrees Celsius have significant effects that are mitigated.
I think we're having some technical issues with Professor Costantino.
That follow these isolators are at load of 10,000 tons. Could not have been tested dynamically anywhere in the world, or in the future. We don't have machines to do that. But we could test reduced size isolators. And for that, one has to develop the theory. It's not just on the basis of opinion, but one has to develop isolators to be tested on the basis of theory that are concave or double friction pendulum isolators. This up almost 20 years ago. So you can see the use in these bearings of 2 sliding surfaces instead of 1, something that almost doubles the displacement capacity for the same size of isolator, but also, very importantly, reduces the velocity of sliding between the top and bottom surfaces of the single sliding isolator. This to 2, therefore reducing the heating effect. So you have 2 main advantages of these: the increase in the displacement capacity and the reduction in sliding velocity, and the reduction in heating effects, which are very important, as we are going to see. Now, the use of this articulation here is needed if you have friction coefficients on the two surfaces that are different, significantly different, not just minute differences. But if